Good evening, ladies and gentlemen. I'm very happy to be here and to present you the FuturICT flagship concept. The European Commission has set up this FED flagship initiative where they want to spend real big money on real big science. They want to have a real visionary project, and we will see later on that it is very important within the context of this project to have a background in the natural sciences, in engineering sciences, and the social sciences. So this project brings it all together. What is this project about? It's basically trying to address the challenges of the 21st century, some of them at least. And we want to point out that there are some old problems, but there are a number of new problems, so we need to change perspective. The old perspective on problems is that there are some external threats to society, but now we are facing intensified and new global problems, such as the world financial and economic and debt crisis. Actually, it has intensified again today because Greece may have actually a poll on the question of whether this European support scheme should be applied or not, and that has really disrupted the financial markets in a very strong way. Then we have social and political instabilities, as we see them, for example, in some Arabic states at the moment, also even in Europe. And there's global environmental change, organized crime, cybercrime, and to mention a fifth example, the quick spreading of emerging diseases. All of that is a result of the strong coupling that we have in our globalized world. So the goal and vision of this project is to better understand society and socially interactive systems in generally, and its dependency on the main driving factors such as resources. In fact, our knowledge of global techno-socioeconomic systems today is quite limited. This quote of Jean-Claude Trichet, the previous president of the European Central Bank, just ended his term, said, "When the crisis came, the serious limitations of existing economic and financial models immediately became apparent." And he continues, "We felt abandoned by conventional tools. That means we need to have a new approach, a new science to understand these kinds of systems," and he recommends that economics should get together with physics, with ecology, with psychology, and so on, in order to get a multi-perspective view on these kinds of problems. Lizzie Bollinger, as president of Columbia University, has formulated the issue as follows. "The forces affecting societies around the world," he says, "are powerful and novel. The spread of global market systems are reshaping our world, raising profound questions. And these are the questions that academic institutions are uniquely qualified to provide." He continues that too many policy failures are actually fundamental failures of knowledge, and that means that somehow it's our responsibility as scientists to create this knowledge. Some of the global challenges that we are facing today can be understood through cascading effects. Cascading effects are difficult to imagine because they can be quite complicated. They don't need to be linear as the kind of the typical domino effects. It can be propagating through networks with feedback effects and unexpected side effects, actually. And each of these steps is usually probabilistic. It already creates quite a bit of problem for us to imagine probabilities, but coupled probabilities in networks is even harder to imagine. And that's why actually those cascading effects are typically underestimated. Some of the network structures we have created actually have not considered even the possibility of negative cascading effects. But in fact now we recognize that many of those network infrastructures created to provide new functionalities and services also create pathways for disaster spreading. And I'll show a number of examples. One of them in a technical system like this cascading effect that created a blackout in the European power grid actually in many different countries. The origin of this blackout was a line that was switched off temporarily in order to allow a ship to pass. And it then triggered off a cascade of switch-offs that created blackouts all over Europe, including Portugal, really a long distance away from Germany. And you can see from those blackout patterns actually that this is really hard to predict, but that feature is typical for complex systems. Here is another example. Cascading effects in the financial markets. We know that the financial crisis started off through the subprime mortgages in the United States. There was a real estate bubble basically. And although this problem was substantial, it could have been dealt with because that budget in principle can be provided by a country like the United States, but politics somehow hoped that self-organization of the markets would allow to fix the problem, and those measures that of course were politically taken, but apparently they were not enough, and so it created a cascading effect that increased the losses in the financial and economic system substantially. And by now, I think it's about 20,000 billions of losses that the financial crisis has created. And it has created a lot of bankruptcies. So I'm showing you here a video that has been created by Frank Schweitzer's team. And it shows you a cascade of bankruptcies in the United States. It looks a little bit like a thunderstorm, but clearly those events are not independent of each other, and you can see that the situation becomes worse and worse and worse, with more than 300 banks that have defaulted in a short time. Here is another example from the area of energy, which shows you the cross-sectional interdependencies actually. So, as you know, we had this nuclear disaster in Japan earlier this year, and at that time I actually already predicted that that would have political impacts, as it happened later on in Germany and in Switzerland, where it was decided basically to turn away from nuclear power production over the next 10-20 years and go into different energy production systems. But then the question is, okay, what alternatives do we have? And I am focusing here on one alternative, which is solar power. Actually, there is a big consortium that's trying to bring up a system that's going to create solar power in Northern Africa, basically for all over Europe. This consortium is called Desertec, but the political situation obviously has destabilized since through the Arab Spring. We don't know how the situation will develop. That means the future of this project is somehow unknown. And we can also say that other energy sources like gas provided from different areas of Europe and Africa. So the major sources are actually from Africa and Russia, also are exposed to political uncertainty. So we can see that here obviously there is an interaction between different kinds of energy, but also between energy generation and on the other hand political factors. And one could go one step further and ask, okay, why has the situation destabilized over here in Northern Africa? And it turns out somehow that we have a cascade of political instabilities which has been framed as Facebook or Twitter revolution, but I would like to give it a different interpretation. I'm pretty much convinced that Twitter and Facebook have not been the reason for the revolution. They may have basically acted as catalysts, but somehow there are social and economic data that indicate that somehow this shift from an autocratic system to a more democratic system was overdue. So what we show here is the GDP per person in US dollars and the fertility, a number of children per woman. And you can see that here is a clear separation line between the autocratic and the more democratic systems. And actually some time back also we had these kinds of transitions in Europe itself. So in principle there is some mechanism behind it. There are some driving factors that promote political changes. It may be difficult to predict the exact moment in time, and it may depend on triggering events. But I will come back to this later on, because this is quite typical for these kinds of complex systems. And here is a graph that actually shows what were the real triggers of these social unrest, which is food prices actually. So you can clearly see when the food prices went up, then social unrest started. One could now go one step further and really ask, okay, why are food prices going up so much? Because on the other hand, the world has produced enough food for even about 7 billion people. And it turns out that this resulted actually from our attempt to overcome global warming, which is a side effect of our energy consumption. And the world started off producing biofuels in order to improve the CO2 statistics and reduce the global warming. However, the production of those biofuels then started to compete with food production. And obviously that increases prices of food. But not only that, once the prices of food increased, it became interesting for financial markets. So financial speculation set in, and that further increased prices, although there was enough food, as I indicated before. So we got these kind of bubbles in the food prices that caused those social unrests. So summarizing this, we have a coupling on a global scale between many different kinds of developments and events in the area of the environment, food production, energy production, a nuclear disaster that happened, and political events and financial markets. So all of that is strongly coupled. And we can understand our problems only if we really understand those systemic couplings. Here's another example that also has characteristics of cascading effects. So this shows violent events in Jerusalem, and as these data suggest, the one event tends to trigger off other events. This is work that has been done with Karsten Donay and colleagues from the political sciences. And now, cascading effects, however, are just one of the mechanisms that explain some of the urgent burning problems that we see in the world. The situation, however, is more complicated than that. Our world has actually become a strongly coupled world. Now we have a global exchange of people, of goods, of money, of ideas, of information. And so that is the result of globalization and technological progress, that we have much more strongly coupled the components of our world. There are much more interdependencies. And what I'm claiming here is that this changes the character of the system fundamentally. A strongly coupled system behaves very much different from a weakly coupled system. And in particular, it becomes a complex system which has those features over here. So first of all, you cannot do a strict system optimization anymore in real time, even with supercomputers. Those systems are just too big, too complex. The strong coupling triggers off a faster dynamics in many areas of our life. We can feel it ourselves. There's an increased frequency of extreme events, and unfortunately they can have basically any size, including global size. The predictability of system behavior goes down. We can have unwanted feedback, cascade, and side effects. In fact, complex systems often behave in a counterintuitive way. Self-organization and strong correlations dominate the system dynamics, and there are very limited possibilities, therefore, for external control. Altogether, also, those systems tend to be more vulnerable, and altogether, that has also an impact on people's trust into public and private institutions. So these are the features basically predicted for a strongly coupled system, but obviously we have all those features in our real world. And that calls actually for a change in perspective. Many of the problems we have, I'm claiming, we have because we have the wrong perspective on those problems and we draw the wrong conclusions. We tend to have a component-oriented view, and it's partly because we see those components. This is what our 5 senses are showing to us. While actually the behavior of complex systems is very much determined by the interactions, as it's being studied by complex system science. So we need to have a complexity science approach in order to understand those strongly coupled systems we're living in. And then the question is, do we have examples for strongly coupled systems? How do they behave? What can we learn from them? And here is a model system actually, where we have table tennis balls on top of mouse traps. And this person will just drop one single table tennis ball to trigger a local perturbation. And you will see that this local perturbation can actually disturb the whole system. So it basically has a global impact. And this is how you can imagine those cascading effects that affect our world. But the question now is, if we have strongly coupled systems, and that is also, by the way, a model of nuclear reactions, and we know nuclear reactions are not so easy to control, otherwise we wouldn't have disasters now and then. So that also means that those strongly coupled systems that we have created in our world are also hard to control. And the question is, did we inadvertently build something like a global time bomb? Almost without knowing, without noticing. And I was not sure about this conclusion. I was thinking about it a lot. I was looking around, and actually this is an article that I found, which was written, interestingly enough, back in 2003 and published by the BBC, a serious news medium, and this is Warren Buffett, one of the richest persons in the world. So he must know something about how the world works. And what he was saying is, the rapidly growing trade in derivatives poses a mega catastrophic risk for the economy. And he was warning of an investment time bomb 8 years ago, and how right he was about it. So I think we need to be concerned about these things. We need to have these new models of thinking about those strongly coupled systems in order to get a better idea what can happen in those systems and why, and also what we can do about it. Here's one more thing that we need to be concerned about, which is the degree of networking. What I'm showing you here is an interaction in a system between individuals that are exposed to so-called social dilemma situations. Social dilemma situations are situations where it's favorable if everybody cooperates. But for you, it's even better if you don't cooperate and everybody else does. So there is a temptation, basically, not to cooperate. And as a result of that, kind of the natural solution of these social dilemma situations is that people don't cooperate. That means there would be an erosion of cooperation, ending up with a tragedy of the commons as we are seeing it in many areas, like overfishing, destruction of our environment, and so on and so on. Exploitation of social benefit systems, non-willingness to pay taxes in some countries, and so on. So this is a problem that is showing up in many places of our society, and I would say also the economy. And without the willingness of people to cooperate, society probably wouldn't work. Certainly wouldn't have those cultural and social standards that we're having today. Now let's see what happens. There are a number of mechanisms that are actually stabilizing cooperation, shown in blue, while non-cooperation is shown in red. And among those mechanisms is actually local interaction with your neighbors. And as you can see over here, under the conditions simulated, eventually this local interaction creates cooperation among individuals or companies interacting with each other. However, now we will eventually link more and more those individuals or companies or banks or whatever with each other, and you'll see there is a moment where the networking is so dense that it triggers a breakdown of cooperation in those social dilemma situations. And one of the questions is, does it have any meaning for our financial and economic system? It is interesting to note, in fact, that our banking system very much was organized in a regional way, say 20, 30 years back, and now it has become a global village where every bank is interacting with every other bank. Has this destabilized cooperation in the system? Has this created the financial breakdown? We don't know for sure, but certainly we need to be worried about these issues. We cannot just go on networking because a little bit of networking is good for the system, and more networking is fine as well, but you know, if we go on like this forever, it could be destabilizing our system from within.
There is some mechanism inside intuition why more networking give rise to this transition to the red. Could that be not actually two equilibria?
No, the situation is like this. The breakdown of cooperation in a fully networked system corresponds to a situation where you don't have any network or spatial interdependencies anymore. So that corresponds to a situation that can be described by a replicator equation or basically by the representative agent model, and this predicts the breakdown. So somehow it is clear that it must happen if everybody is connected with everybody else. Here's some other examples. So if you found this example too theoretical, I'm showing you a self-destabilizing system over here where cars are following others and trying to go smoothly ahead. But as you will see, they will fail. So at one moment in time, there is a perturbation because it was an unattentive driver, and now we have a traffic jam, as you can see over here. This traffic jam is moving backward, by the way, but we don't get rid of it anymore. And actually, as I will tell you later on, it reduces the capacity of the system. This can be understood actually based on mathematical equations. And I show you again another example, like pedestrian behavior. You will see over here that oppositely moving pedestrians are not just moving through the other crowd in an arbitrary way. Instead, we find a nice organization into uniform lanes of walking direction. And in this way, those different directions of motion don't obstruct each other a lot. Instead, we have a very efficient motion. So we could take that maybe as an example of Adam Smith's invisible hand phenomenon, where by self-organization, the system ends up in an optimal state somehow, optimal organization. However, we know when the density goes up too much, then we can get into this situation over here, which very sadly ended up in a tragedy, in a crowd disaster where many people have died. This is a movie from the Love Parade disaster in Duisburg, but as you know, there have been many crowd disasters in the past. So again, the self-organization, the favorable kind of self-organization, can break down if you overload the system somehow, if you stress it too much. So the question is, could that also happen to our economy, where we believe that Adam Smith would be at work? Could it happen that if we stress the system too much, Adam Smith doesn't work anymore? That means if everybody is just doing the thing which is best for himself or herself, that would not necessarily create the best situation for the economy or society? Well, at least that's a question we should ask. I've now shown you quite a number of worrying examples, and you could maybe get frustrated about it and depressed even. So the question is it a lost battle against this complexity that we're facing? And I say no. It just requires a different kind of understanding and a different kind of approach. We need to have a paradigm shift towards flexible, agile, adaptive systems. And this is possible and overdue. By the way, that is an old slide which I've shown 2 or 3 years ago, where I was already pointing out this top-down control that we have basically in many countries is enormously costly and not necessarily very successful, because a society is a complex system, and from that perspective it's hard to control from the outside. So we need to have a different approach, and the approach that I'm trying to promote over here is to facilitate, to support self-organization of the system. That means let the system do the organization. You just have to fix the right interaction rules for that. And I will show you examples later on. But here, another quote of somebody I have a high opinion of, Sandy Pentland from the MIT Media Lab, has in a shocking openness pointed out that our financial, transportation, health systems are broken. I've never heard anybody before saying it so openly, and nobody objected against it. I said, somehow he's right, and probably there are other systems we have to add over here. He continued, we need to develop a decentralized adaptive approach in order to manage the complexity of those systems, and this requires real-time data mining. And in fact, there are a number of examples where we have been successful overcoming those classical problems, such as crowd disasters. The most difficult site actually where crowd disasters have happened recurrently in the past is Mina, very close to Mecca, and there is the Jamarat bridge. The situation was really extremely crowded in the past, and that caused a number of crowd disasters where hundreds of people have been dying. Now, how could this problem be solved? Well, first of all, the flows were reorganized in order to avoid crossing and counterflows. Then moreover, we introduced a real-time monitoring of the flows that allowed adaptive rerouting, and contingency plans were developed for all kinds of situations. So there was a plan B and a plan C, and maybe even more plans in case something goes wrong. You don't want to improvise in such a situation. You want to have a fully developed plan and just apply it. Why didn't we have it in the financial system? Here's another example. Traffic light control in cities. Everybody is annoyed about congestion in cities. I will show you later on that actually if you control the system the wrong way, it will lose a lot of capacity actually. And so there is a new approach that we're pursuing. The classical approach is that you have a supercomputer that is connected to all traffic lights in the city and is controlling their behavior based on measurements of the traffic flows. However, the traffic flow program has somehow been optimized for a typical situation. And that typical situation never occurs. Even when you adapt your traffic light control a little bit to the changes in the flow, that will not actually solve the problem. We have taken a completely different route. We have said, okay, let us rather respond to the actual traffic situation, even if not 100% optimally. If we are 90% optimal to the actual traffic situation, is better than being 100% optimal to a typical traffic situation that never occurs. And in fact, that could be implemented with a real-time measurement of inflows that allows us to make short-term predictions of platoons of cars arriving at the traffic light. So we would basically create green waves. And it is very important actually over here that there is coordination between neighboring intersections or traffic lights of neighboring intersections. If traffic lights at each intersection are controlled in an optimal way, strictly optimal, like kind of the paradigm of the Homo economicus would require, then it turns out that you don't get a system optimum. If you want to get into a situation where each intersection and the whole system really perform well, then it is required that each intersection somehow is coordinating a little bit with the neighboring intersections. And then this coordination in our system is spreading through self-organization all over the system. And it creates a situation which is beneficial for all modes of transport, beneficial also for the environment, creates shorter travel times, more predictable travel times, and a better use of scarce resources, in this case space and time. So it's like a magic formula that allows us to get more out of the same system. We also made progress in terms of understanding conflict. The Middle Eastern conflict is a conflict that is worrying the world since a very long time. It has implications for the peace in the world, and so it's very crucial to understand this kind of conflict. And in fact, with agent-based simulation, we can get a better idea, and those agent-based models could be made realistic through those new data sets that are now becoming available about real conflicts. This work has been done again with Karsten Donai. And what you can also do, you can basically simulate different political scenarios, like go on as usual, or the Clinton scenario, or some other scenarios like going back to 67 and so on. You compare those scenarios and see what are the expected number of fatalities in the conflicts. You don't get rid of conflict and violence completely, as you can see over here, but you can considerably improve the situation through the choice of the political scenario. So there are a number of really interesting success stories. And now the goal of this FuturICT project to scale it up, to bring together the best knowledge of engineering sciences, natural sciences, and social sciences in order to speed up innovation and get into a position to catch up with upcoming new problems.
When you say there are success stories, in particular in the political situation of regenerative model, how do you validate the simulation? So you can indeed simulate as much as political scenarios. And
This is a very sophisticated procedure, and it's written up, I think, a 50 or 60 page paper that certainly we can share with you. No, basically you have to compare your simulation with empirical data, but we do more than just fitting parameters of a model in a way that makes the model produce your empirical data. You want to know somehow the statistical validity. And so basically you have to do some permutations and to have somehow a procedure that allows you to test the significance of your simulation model. It's a sophisticated point. I don't think I can explain it within a minute over here. So we will bring together those different fields of science, and in particular the computer science, information and communication technology with the social sciences and complexity science. And the goal is to come up with scientific, technological, and societal outcomes such as the ability to understand our global techno-socioeconomic system, new ICT platforms for collective awareness and participation, and also the ability to manage our global system towards a more resilient and sustainable society. I'll go into more detail now. So first of all, there has been actually a lot of progress recently in the social sciences, also in quantitative social sciences, and basically we expect there will be a new era of the social sciences created by the possibility now to bring experiments, big data, and computer simulations together. Now, FuturICT is a really ambitious endeavor, and it involves a number of different activity areas. And I'll try to explain it a little bit in more detail now. So, there will be exploratories of society, of economy, of technology and environment, and those exploratories will be created by integrating a number of observatories of financial systems, of economic system, of health, of conflict and war, and so on and so on. So that will be built around colleagues who have been successful in pulling together a lot of data sets, analyzing them, visualizing them, and simulating models of these kinds of systems. And now we have to bring this knowledge of the different fields together in order to be able to gain a systemic overview of what is happening in the system. So there will be this observatory for financial instabilities that Didier Sonnet will be leading, an observatory for wars and conflict that Lars-Erik Sederman will be leading, an observatory for epidemic spreading health reset Alex Vespignani will be leading, Observatory for Environmental Change, and Transport and Logistics Observatory that Kai Axhausen will be leading. So all of that and many more observatories will be integrated over time into these exploratories, and finally everything will be integrated in one big system that is able to study the interactions between those different sectors of our world in order to get this systemic picture. And then we'll bring together big data with computational analysis of these data in order to detect possible warning signs of instabilities, to do large-scale simulations, but also to create participatory platforms that allow us to explore interactions in possible societal forms of organization, and so on, in order to be able to have a better informed political decision making. But the goal is not to have a system that would tell politicians what to do. It's more about creating new instruments, like people have created microscopes and telescopes in the past, new instruments to get a better overview of the system and to be able to get different perspectives of the system. And this system could be used, actually, this platform could be used by not only politicians and business people, but actually by everybody, as everybody now is using the internet to his or her own benefit. So key components, particularly key methods and instruments we are creating, kind of these telescopes for socioeconomic systems, will be a living Earth simulator that will be there to model the systems, a planetary nervous system to sense and understand, and a global participatory platform to explore, interact. And I'll go a little bit into more detail. So people are sometimes asking, okay, can you really simulate systems that are complex, such as social systems certainly are very complex, and I'm showing you one example where we have been extremely successful, although if you look actually at empirical data, it looks like it would be hopeless to find a mathematical model for that. Actually, we would have given up right away if we had seen those pictures in the beginning of our traffic research. Fortunately, we didn't have those data at that time. So what in the meantime we managed to come up with is an understanding of the complexity of those patterns based on elementary congestion patterns as they're shown over here. And besides, we have obtained a theoretical understanding under what conditions those different kinds of elementary congestion patterns can occur. Free traffic, stop-and-go waves, homogeneous congested traffic, and so on, moving localized clusters, all different kinds of traffic jams. We were actually surprised to learn that there were so many different kinds of traffic jams. But now we understand the conditions under which it happens, and very interestingly, there are conditions under which there can be different kinds of outcomes. So we call this multi-stability, and the outcome is history dependent somehow. So it depends in particular whether disruption in traffic flow is small or big. That can make a big difference, and the situation that we can have different outcomes can be very confusing actually in those social, economic and political systems. So that somehow allows us to understand some inconsistent findings that are so typical for social systems.
Here, just with a bit more meat on this diagram, so you show many coexisting things. So what are the two axes? One is flux and the other one?
This is the bottleneck strength over here, or the inflow of vehicles over an on-ramp of a freeway, and this is actually the upstream freeway flow. And the sum of it is actually the overall traffic volume. Here is an example that shows you how counterintuitive actually traffic systems can behave. This simulation is for a freeway with an on-ramp at kilometer 0, the mean over here. You can see that the density is a little bit higher downstream of the on-ramp, which is logical. And you can see, however, also that the density is actually stable over time. Yeah? So we have free traffic flow over here. And then we perturb this free traffic flow by reducing the density in the flow. So we would think that should actually improve the traffic situation. Instead, what we find is that this perturbation is triggering off the breakdown of traffic flow. Why is this? Because traffic can behave in a metastable way, and there are regimes, density regimes, where supercritical, that means large enough perturbations, can trigger a breakdown as we see it over here. It can be even a negative perturbation. So what happens is this perturbation moves forward, this lower density area is being filled by cars moving in quickly, and then that creates eventually areas of higher density. But look, this perturbation has already passed the bottleneck area. So we would think, okay, we got rid of the problem, but what happens now is that there is a boomerang effect and this whole perturbation turns around. Why is this boomerang effect? Well, as long as the perturbation is small, you have an area of a higher density of cars that moves forward with the cars. But as soon as you have a big perturbation, you basically have a traffic jam where cars are stopped within the traffic jam, and that means that cars are moving out in the front and other cars are added to the jam in the end, so altogether that's moving backward. That means there must be a transition from forward motion towards backward motion, and that's what is happening here. Now, at the time when this traffic jam, this moving traffic jam is arriving at the bottleneck, we see that traffic flow breaks down. We did not change the inflow at all. That means we have the same traffic volume in the system. But the fact that now we have a queue of vehicles forming behind this bottleneck of the on-ramp shows that the capacity of the system has dropped. The very same road that managed to carry 2,500 vehicles per hour and lane now only copes with 1,800 vehicles per hour. That is shocking. The very same system has a lower capacity, and actually this breakdown of capacity happens when the system reaches the point of highest efficiency, that means of highest throughput. This is the point that in economy we always try to reach. So once we reach this optimal point, our system performance breaks down, and we have this problem of the traffic jam resulting from this breakdown of capacity. In principle, if we manage to stabilize free flow, we could get rid of this traffic jam given the flow conditions. And my assumption actually is that recessions are maybe a similar problem, that the very same system suddenly doesn't have the same performance anymore. It has a completely new perspective on old problems. Now the question is, how is all this triggered? You've seen actually this simulation over here. You could say, okay, maybe this is just an artifact of a strange model, but in fact, here are empirical data, and you can see that we have quite a number of examples where we have exactly this small perturbation that turns around and eventually triggers off a bigger congestion. And if you analyze it more carefully, it turns out that in many cases actually that is triggered by trucks overtaking each other. So we can identify the trigger of these events. But in principle, before the breakdown and after the breakdown, we can predict travel times very well, as we can actually make reasonable predictions about the traffic pattern. So there is a lot of predictability, just we don't know the point in time when the supercritical perturbation takes place. Still, we can calculate or determine the probability that this breakdown will happen after within 1 minute or 2 minutes or 5 or 10 minutes. So we can give a probabilistic answer actually. And we are able actually to simulate, at least qualitatively, those different kinds of elementary congestion patterns and more complex patterns as well. So by now we have the possibility not only to simulate all those patterns, but also to analytically understand them reasonably well. And in conclusion, there are basically three preconditions of congestion. which is lack of capacity, high flows, that means high interactions or strong coupling, and third, perturbation of the traffic flow. And my belief is, or conviction, that in many socioeconomic systems we have somehow a similar situation, that it's possible to do short-term predictability, even though only in a probabilistic sense. The system dynamics is determined by the contextual settings, interactions, and random events. And I am furthermore claiming that this knowledge can help to improve system performance. I have indicated already before, in principle, the very same road could carry actually more vehicles and we could get rid of the traffic jam. How can we do that? Well, basically, when starting off with today's traffic situation, which comes with stop-and-go waves as they're simulated over here, we can think of changing the interactions of vehicles a little bit through driver assistance systems, which are changing the interactions of vehicles. Now we have actually turned on the system. You can see that the stop-and-go waves go away through changing the interactions between vehicles. That means my claim is that in order to solve many of the problems we're facing today, we have to focus on the interactions and find the right interactions to allow the system to self-organize well. But not only do we want to simulate, we know that simulation still is limited somehow by the fantasy and creativity of the researcher, and it can happen that somehow you miss out an important detail. In order to avoid that, basically, we want to have an environment that allows to explore the interactions of people. We call this populated virtual worlds, something like a multiplayer series online games where people really interact with each other, and we could actually check out different worlds, different futures by implementing one financial system in this world and another financial system in this other virtual world, and so on, in order to find out which system is the one that performs better. And then we could choose basically that world and try to implement it as good as we can. Of course, all these simulations and all these virtual worlds require a lot of data in order to be set up. And where do we get these data from? Well, basically now they're becoming more and more available through all sorts of technologies, and that allows us to put them together in order to create something like a planetary nervous system even. We could also set a new system that allows us to collect additional data. Everybody's smartphone actually has a lot of sensors that allow us to collect data. We just have to make sure that people would voluntarily provide them, and in order for them to do that, we have to take care that we won't interfere with their privacy. So we have to come up with technologies that would protect privacy. We have to come up with incentive mechanisms, so people who would contribute data should also participate in the benefits, and so on and so on. So these are really some information and communication technology challenges that need to be addressed. But there's a number of interesting applications already, like OpenStreetMap or collective earthquake sensing and warning system, that are based on such kind of decentralized applications. And we can do more, and that's actually the reason why we're talking about a planetary nervous system, because somehow we can use the system to get an overview of the state of the world and create collective self-awareness of the implications of human decisions and actions. So we want to get into a position that we can provide new compasses to decision makers which are better than just GDP. There have been commissions like the one set in by President Sarkozy involving Nobel Prize winners who were trying to identify better indices that take into account health, environment, happiness, and these kind of features. So basically, other kinds of capital apart from economic capital, including social capital such as cooperativeness and trust and so on and so on. So in order to protect these kinds of capitals from being exploited or destroyed, it's very important that we become able to measure this, basically to measure the social footprint, and that will put us in the position to protect the fabric of our society as we have learned to protect more efficiently our environment by quantifying the environmental footprint. I'll now skip over a number of slides which basically go a little bit into details about how the implications of our decisions and actions on the world can be studied. So that requires to learn about causality networks. That means how one thing leads to another, and there are also models for that. This very much depends on actually the network structures. One important implication for recovery from disasters and is, for example, that it's very important to respond very quickly to the disaster. Another lesson is that rather than running behind the course of events, you should try to anticipate what would be the next endangered areas of society or technology or economy that is endangered basically by those cascading effects. So you could try to protect those areas and thereby stop the cascading effects. And in fact, it turns out that the strategies that you should apply to stop the spreading of disasters very much depend on the kind of network you're facing. Very important also is to have decoupling strategies in place. As I said before, cascading effects actually are one of the reasons for the size and costliness of the disasters we are facing. And so it's very important that you can stop those cascading effects. And for example, we are doing that in our electrical systems through fuses. If there is a local problem, they will stop the propagation of the problem in the system. And we have similar things in our computer system, like firewalls. So the question is, couldn't we implement such a decoupling strategy in our financial system, for example? I mean, now maybe it's too late, but in principle it's a bit surprising that the cascading effect really could spread so widely and produce so horrible cost to our society. Finally, there is one activity in this project where we want to create open, transparent platforms for everybody. So we want to overcome black holes for data. We want to provide platforms with data for everybody and mechanisms that stimulate responsible use. That is important because we're talking about the creation of a new public good. And so there is a potential problem that data may be polluted or manipulated, or a system may be misused, privacy intrusion, cybercrime, all that needs to be kept small or avoided, and that requires some thinking about how to design this kind of system. And basically we imagine as like a self-regulating ecosystem or immune system that would basically create a new internet, the future internet, which we call the trustable web, which would be based on reputation mechanisms, for example, and protect privacy and so on. So there will be huge benefits of this project because the losses through the financial crisis, conflict, terrorism, and many other problems are really so outrageously large. Each of them amount to trillions every year. So if we could reach a 1% improvement, that would really create a big improvement for the world. And besides, also, we believe that creating these tools and also this platform, this new information ecology, basically, will create a new basis for a lot of new businesses and applications and services and so on. So in conclusion, this project is building on fantastic science. It has been published in the best journals, actually. The project will fill many knowledge gaps, such as creating a non-equilibrium economics, create knowledge about systemic risks, integrated risk management, and so on and so on. So basically create knowledge on systems, where we have the biggest knowledge gaps right now. And a number of new technologies, such as the open data platforms, the privacy-respecting data mining, trustable web, and ethical ICT. But the most important message, the take-home message, is that we need to change our thinking about our world. We're not living anymore in a weakly connected or weakly interdependent system, which is dominated by the properties of the system components, and where our conventional wisdom works well, and also the conventional control strategies work well. Now we have created strongly connected and interdependent systems, and those are dominated by the interactions in the system. And that creates complex system behavior, emerging collective behavior that is often unexpected, and in many cases, extreme events and so on. Those systems are less predictable, but not hopeless. And we can manage them by setting the right interaction rules for bottom-up self-organization. So many of our current and future challenges cannot be solved within our current paradigm, but the paradigm shift towards this, focusing the attention to the interactions, will create new solution approaches as actually the transition from a geocentric worldview to a heliocentric worldview was the precondition for modern physics and our ability to shoot satellites into space. Thank you very much.
Thank you very much for this fascinating talk. I propose that we take another half an hour for questions and answers. So, who is the first? Can you please give your name and affiliation?
Yeah, I'm Hugh Lutzner, and affiliation, I'm not with any university. I'm here as a private person, you might say as a taxpayer. And my question is really, when I hear your talk, there are many things which are quite reasonable, and everybody would agree on this. But then, time and again, I see a leap in complexity in your systems you're describing. For example, you had this example with the traffic system, and then you said, yeah, that's the same like a recession, or that's similar, or that's your belief. But it wasn't clear to me from the talk why there are such close similarities between completely different systems. That's a very tough statement, because in the end, the statement would be similar to, yeah, the world is not really complex. There are certain patterns which you have to organize in a clever way, and then everything is simple. And to me, that's not obvious, and to everybody else, or to many people as well. The second thing is, when you talk about the future,
Shorter, so not too many comments.
yeah, sure. The future ICT descriptions are very general. It is completely open what a planetary network is, or what reality mining the planetary network means. And as a personal remark, I feel my bullshit detector really ringing on this. Yeah, I mean that's my personal feeling, because they're very general and dark notions there. So
Can you comment on that?
All right, so first of all, you need to see the following. Many of those examples I've shown, and this is just a selection of what I've been working on in the past, are example of my own work, a single person's team. FuturICT has 900 teams behind it at the moment, from the best academic institutions all over Europe, and it has supporters in the United States, in Japan, in China, Australia, and so on and so on. So if you scale it up, you see you can really go into much more complex systems. I'm not claiming that this is just the same model and you have to change the names of the variables. This is not what we have done in the past. So you need to study those systems, and that requires, of course, a lot of data. But what will really allow this paradigm shift in science to happen is that those data that have been lacking in the past to make the progress are now becoming available. This is the point. We are overwhelmed by data almost. So this is one issue. There's also, in fact, there's a reason why I say there's similarities between systems, because complex systems have been generally studied with regard to the possible phenomena that can occur in those systems, and there are kind of universal behaviors that you can find, a certain number of possible behaviors somehow, and these behaviors result from certain kinds of interactions, and it is somehow expected that you find some of those behaviors in the real world. So you need to know more about this kind of science and about universality to understand it, but there is a reason that we can believe that this is doable. Not only we believe that, actually, there is Microsoft modeling the world. They want to make big money out of this. There is actually the American government doing these kinds of things hidden from the public. We want really to give these kind of tools in the hands of the people. This is important. Also, we are not the first to think about the planetary nervous system. This idea has been first pushed forward at the MIT, the most famous IT institution maybe in the world. So that is also triggering all the new technologies for IT companies all over the world. You need to be aware how quickly our information and communication technologies have changed over the past 10 years. Actually, it's hard to remember that, but if you extrapolate that into the future, considering that 5 years ago we didn't have iPhones, we didn't have Facebook, we didn't have Twitter, then it's really hard to imagine what the situation would be in 10 years. So what seems to be fantastic from today's perspective will become doable within 10, 12 years, which is this period of the project. We need to consider that.
Well, I would propose to be a little shorter with the questions and the answers. So, next question. Yes, please.
Peter Scholz, I work in the GSO Institute. Are you sure that if you have a policy, if you have new ideas of policy, that it will be politically implemented? Because you have like very common sense things like in the US where you have this obesitas problem. You don't have a big system. You don't need a big system to know that it is there, but there is nothing being done politically. So how sure are you that in the end your conclusions will be politically implemented when you see that even common sense things are not being implemented?
Well, there are a number of reasons why I believe this. First of all, for a good idea to be implemented, it requires visibility of this idea. That's the first thing, and it does not apply to a lot of science. So a lot of great inventions in science require 30 years to be implemented and applied. Because of that, this lack of visibility, and FuturICT will have the visibility required. And I am already approached actually by people from the political sector. They're noticing this project and they want to learn about our way of thinking. The other point is that we are more and more running out of options. In the way we are governing the world these days, you know, we have used more or less our alternatives. What else can we do to really cope with the financial crisis? And there are not so many options. So there will be the point where we need to have a new approach. And that day will come, basically. So science should be prepared for this day to have the draft of a plan B, basically. It would be really terrible if the financial system crashes, which is not completely impossible, and we don't have an alternative. So humanity needs to prepare and have a plan B, a plan C, and have these contingency plans in place, and we are trying to work on that.
Coming back to your point, indeed,
So this is the from
yes, and the recent
and the risk center.
yes, like you and yeah. Coming back to points, coming to questions. The analogy between recessions and traffic jams is an issue. For example, Hans could, for example, invoke, or also Antoine, the fact that there is a very well developed body of literature associating recession with the business cycle. That I don't see the analogy of the business cycle. You have to explain maybe the analogy of the business cycle. You know, the inventory build-up, the delays in reaction. So that would be an analogy actually. But also the recession comes, and there's a very nice empirical cartoon or graph that shows it. If you look at the long-term GDP growth of countries like US or European countries, you see more or less an exponential growth. But it's actually not following a smooth line. It's overshooting, then recession or plateauing. Overshooting, recession, plateauing. Overshooting, recession, plateauing. Very clear. So you could say that there's a kind of built-in process by which the economy is overheating, there's upgrade, there's new economy value, there's, you could say, bubble theory or a mechanism of political mechanism, many, that makes the system actually grow faster than actually on the long term it's able to do. The recession are part of this process. So I think there's much richer zoo of behavior and mechanism than the analogy. So that's the thing we want to combine.
Yeah, actually, it's nice that you mentioned that because we have not just claimed it like this. I've been working on models for business cycles that are based on supply network models that are kind of models that look at how flows of goods happened between different sectors of the economy in a network. And you can find exactly those kind of instabilities. So I'm not just saying it. I mean, there is scientific publications about these things.
Okay, another point, the second point is you promote this bottom-up, decentralized way of regulating, of control. Great. And in addition, you make an analogy with ecology, with spaces. Do you realize that ecologies are harsh and emotional? This is the battle of life and death. This is, I mean, you know, we want to be in a world which is, you know, with social responsibility, which cares for the poor and the weak. Ecology dynamics is exactly the opposite. It's a selection of the fittest. It's a selection of those who, you know, like it's a free market to the extreme. And so I see a kind of contradiction, and actually an intrinsic contradiction between a control society that, if you think in the end controlled by good tyrants, let's say, who would top down try to make everybody happy, to smooth out fluctuations, as opposed to a bottom-up approach, ecological approach, where you would eliminate all weak people. best of both worlds.
Absolutely,
Yes.
yes.
And that's the question, is it possible? My belief, there's a fundamental impossibility in having both together. You can probably combine a little bit, but this is a very big issue that you are putting on the radar, the research, and I think if you don't realize this major collision between this problem, we are going to be very naive. So it's not one way or the other, it's in between, and this raises the question, coming back to economic thinking, of what are the utility functions? Are they individual utility functions, collective utility functions, global? And we know that they are incompatible. Very well proven also from deep theorem from decades ago. So again, the problems are much more involved and complicated, and so we need to embed all this into a much bigger point of view.
Yes, absolutely. I agree actually on this. And I was mentioning ecology as a complex system mainly because that's a complex system that is better understood today than a social system. So it can help basically build an intuition for social and economic systems to a certain extent. But I agree also there are important differences. So humans have created culture. Culture is made up, for example, of social norms. Social norms make us limit our behaviors. It means we decide not to do certain things in order to comply with social norms. And it turns out that this actually is important for society and social well-being to flourish. And in society, by the way, we also have actually this combination of bottom-up and top-down. So there is this cyclical feedback effect that there is a lot of bottom-up self-organization, but that creates a collective state somehow that again influences individuals' behavior. So we think that actually social system understanding will be more powerful than biological or ecological systems understanding. And this is exactly what this project is aiming at, to gain that understanding. And we'll have also a lot of interesting new applications in the area of technological systems and so on. But I should say that we are not in such a premature state of understanding social systems. I've been working exactly on these issues as well to understand how do social norms come about, when do they come about, and is it in contradiction actually with this classical notion of Homo economicus? And we have extremely exciting results about this, which shows that under certain conditions, moral behavior would emerge in a situation that starts off with selfish individuals, and it would eventually spread in society and be beneficial for society and the individual. So we do have this innovative understanding that is required in order to get a picture not only of an interactive physical or biological or ecological system, but to understand in particular the social nature of the system. And this is important. I wouldn't propose a project if I wouldn't have all those components needed in order to tackle those problems.
where you have venture capitalists funding a lot of companies, and then Google will come up with one or something. So is there intrinsic in the future ICT project something like a multiplicator where you can say we actually encourage this kind of dissemination of these observatories, for example, or is that something which is hard to achieve within that kind of funding?
No, this is exactly the point. I mean, if you want to make such an ambitious project, you cannot do everything yourself. But you're creating a vision that many people and companies are following. So what is important to create these open platforms that allow many people and companies to contribute, basically. So this Living Earth simulator, for example, will of course require a lot of simulation modules for many different areas of society, technology, economy, and so on. But in principle, those will be created by teams of many academic institutions and also by companies, could be also from the United States, from India, from China, and elsewhere, because we'll have this open platform, like an app store basically, where everybody who has created a simulation component can put it there, earn a little bit of money from everybody using it. And in this way, like the app store is working today and comes up with thousands, tens of thousands of different applications, you know, a lot of different people, institutions, organizations, companies will contribute to it, to build it jointly. So it's very important that we create this crowdsourcing approach that allows many people and companies and institutions to contribute, and also many people to use the result.
Jams, we can improve, we can better interaction, we can design a way to control traffic in a more efficient way. But at the same time, okay, the worst system breaks down, maybe the worst outcome will be really bad. Because if we go either try to develop traffic jam in a unstable solution, or design an unstable system that we try to stabilize best way, and then it turns out, it seems quite intuitive that the worst outcome in case it destabilized would be really bad. So, I mean, in your example, it was not so clear for me that you were kind of reducing the risk in all this way.
All right, so complex systems have this feature that they often can go into different kinds of states. And there can be regime shifts between those different systemic states. Those regime shifts, however, happen at so-called tipping points. And as long as you're not close to a tipping point, a system is stable. It means if you perturb it, not more than this tipping point is away, the system will go back to the previous state. I mean, from that point of view, it's pretty stable. It's self-stabilizing somehow. But you need to make sure that you never get to this tipping point, because that will create a transition to a different state. If you don't want the system to get into this different state, there can be reasons, you know, because that state may be beneficial. So, but in principle, if you understand the rules according to which those systems behave, you can take safety measures in order to avoid things happening that shouldn't happen. And it's very important that you don't go close to these tipping points, as it happens when you go towards the point of capacity in many systems. Right? You need to keep a safety distance to these points.
Understanding is always limited. So we go to the efficient systems which are fundamentally unstable but made stable because of the
I mean, certainly, one principle that I would always apply is to have a contingency plans, yeah, adaptive plans in order to cope with also unexpected situations, and to have decoupling strategies that allow you to stop cascading effects in the system, because that is what turns a local problem into a big, 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 big global problem. So that is a matter of how you design the interactions between those system components. You must be able to cut them if certain things happen. And then you can contain the problem. But certainly, I'm rather a person not taking big risks. Certainly not proposing these kinds of approaches to take bigger risks.
Okay, I would like to take one or two questions. Do you have another one?
I understand the difference between small science, having a specific system, studying deeply, coming up with certain equations, simulating it, understanding it in the end, and a big science or the big vision you are proposing. I don't still don't understand the connection. And things you mentioned right now, decoupling the systems, in a way, makes this big science again into small science. And these are not very deep questions. I mean, if you have too much interactions, just disconnect them. I think there are good reasons why the world isn't that simple. And still, it needs convincing what are the common characteristics and why this project will be able to describe and understand them. So, in a way, my question is, what is the unifying idea behind FuturICT? Because there are so many people all over the world doing science. Yeah, okay, that's great. But what makes it a unique project?
So the point is really the change in perspective. Most scientists don't have a complexity science perspective, and they have the component-oriented view. Complexity science is basically not taught at universities, neither in economics, nor in engineering, nor in political sciences, nor in many other fields. And I think if somebody learns about complexity science, everybody would agree that this would have to be part of the course schedule of the education and training of all those people. So there is a lack of certain techniques in a whole range of areas, and that's why we need to have this new approach in order to fill the gap in understanding. It's a different perspective as it's changed from the geocentric to the heliocentric worldview, and it will take a rethinking. For me, it does not require big science. And I'm happy with my own institute, and this is not the issue. But the world is facing big challenges that cannot be addressed by a single team, by a single university or a single department. It requires really many different disciplines and many teams all over the world to work together in order to come up with better solutions. Because we do have this systemic interactions and systemic complexity. It's just too complicated for any person's brain. It requires new tools, and the classical research approach is in economics and many other fields is, there are 1, 2, or 3 authors publishing a paper together. There are other fields in science. There are 20 authors, like systems biology, or maybe 100 authors even. Now, if systems biology requires such an effort, how much effort would it require to understand our real world, our society and economy? Now, I'm maybe intelligent enough to understand certain crucial mechanisms, but I don't claim that I could do it myself. Otherwise, I certainly would not spend 10 hours a day organizing a project, and wish I could spend the same time on science, but I'm doing it because I'm concerned about our future. And because I see that the financial crisis that we're confronted with at the moment has the potential to endanger everything that humans have created over many decades. If we can't stop the crisis, and today there was this other surprise that, this safety umbrella that has been constructed under pain of many European countries suddenly has been questioned. We don't know what will happen. So there are many dangers still that the financial crisis will further spread. And then what would be the implications? The implications would be an economic recession, depression even, maybe even a very serious economic depression. It would be more crime, more violence. There would be political extremism. People would say, we need a strong person to lead us through this crisis. And there could be even worse things. So a lot of this peaceful, friendly, optimistic interaction between people that is characterizing our feeling of life and the society we want to live in is in serious danger. The cultural heritage that we have created may actually be broken within just a few years. This is something that doesn't have to happen, but something which is pretty close and could very well happen to our societies. And it is this concern that makes me spend so much time on this project, that I think I want to try my best to make a contribution to avoid a worst-case scenario. And there are many scientists who actually are also very much concerned, and investors like George Soros and Warren Buffett and so on. They know what is at stake.
Well, this brings us to the end. I would really like to thank you, dear